Okay, the question I want to do, the example is number 2 on this sheet that we were using the other day. Okay, so it says a 9 kilogram sign is hanging from the end of a horizontal beam as shown in the diagram. Now maybe you can't see the diagram, but I can, so let me just sketch it bigger for you in case you can't see it there on your sheet. And yes, I'm being sarcastic, I forgot to put it in. So here's the beam, horizontal beam, and it says a 9 kilogram sign is hanging from the end. So here's the sign. And the sign might say like free pizza. Okay? So there's a weight of the sign here, FG of the sign. From a horizontal beam as shown, the wire attached to the beam is connected to the house. So there's a wire from this end going up to here. Okay? To help support the sign, the tension, what is the tension in this wire if the beam is uniform? So if it's uniform, it means FG of the beam is halfway in the middle. 3 kilograms and 4 meters long. So the full length of the beam is 4 meters, which means this distance will be 2 meters. The FT will be here pulling up. And we're given that the mass of the beam is 3 kilograms. The mass of the sign is 9 kilograms. And from the diagram, it doesn't say it in the question, but on the diagram it shows that the angle is 30 degrees. Okay, so you might think that these are the only 3 forces, but they really aren't. Okay, so this is the house or the wall or the pole or whatever the beam is attached to. Okay, and whatever the beam is attached to here must be also putting a force on this beam. How do I know that? Well, because the tension might be able to balance out the FG of the beam and the FG of the sign, but there's an X component of the tension, right? There's an X component and a Y component because it's at an angle. And the X component is pulling the whole system in. So if the house or the pole or whatever it's attached to isn't pushing out, then this whole system's going to move this way. The X forces aren't balanced. So I happen to know that there, and it doesn't say, does it, from a horizontal beam attached to the house. Okay, so the house, I happen to know, is pushing out with a force here, F house. Now, because I'm old, I know that it's probably going up, that it's not just going out. I know that because it's really hard to just make a force go outward when you're attaching something to a vertical structure. So it's going to go up a little bit as well. Okay, so we have 4 forces. We're looking for the FT. And, okay, and so we will do sum of the torques will equal 0. And there should be a torque for every force, at least in theory. So the tension torque from the house, the torque from tension, the torque from the weight of the sign, the torque from the weight of the beam. Now, after you list your torques like I just did, then you need to decide, where do I pick my pivot point? And in theory, you could pick it anywhere. But there's always going to be a spot that makes more sense and a spot that will be easier. Hopefully you would see that you want to pick it here where the beam is attached to the house for 2 reasons. Because you should be able to see that these other 3 forces would make this beam rotate around that point, right? If FT isn't big enough, this beam's going to begin to move down. Okay, so that's one reason. The second reason is we don't have a clue about this force. And because we don't have a clue about this force, we're going to have 2 unknowns if we pick our pivot point anywhere else. But if we pick our pivot point here, it's going to get rid of this force that we don't know. Okay, so pick your pivot point at this spot and the torque of the house disappears. Then do your directions. The tension is going to make my pen rotate counterclockwise, which is positive. The 2 FGs are going to make it rotate clockwise, which is negative. So it'll be positive, negative, negative. So now fill in what the torques are. So torque is R, tension, F, tension sine theta tension minus r of the sine Fg, because it's the weight of the sine that's causing that force, theta of the sine, minus r of the beam, another Fg, because it's the weight of the beam, sine theta of the beam equals 0. Okay, so first step, list all your torques. Second step, where's my pivot point? For two reasons, so you can cancel out the ones that will go to 0 because of where the pivot point is, and so you can get your positives and negatives on the other one. Once you have that, now fill in your RF sine theta for each one. Now you look at the thetas. Are any going to be 90 and therefore go to 1? Yeah, these two are. The Fg of the theta of the sine and the theta of the beam are both 90, so those are both 1. But the tension isn't, so this sine theta has to stay. We're solving for Ft, so take these two terms over and they're going to become positive. R of the sine, M of the sine, G, sine theta is gone, plus R of the beam, M of the beam, G, sine theta is gone, it's turned to 1. And then we're going to divide by R tension, sine theta tension. And now we're going to fill our numbers in. So R of the sine, how far away is the sine from the pivot point? It's 4 meters. Mass of the sine, 9 kilograms, times 9.81 meters per second squared, plus R of the beam. It's a uniform beam, so its center of mass is 2 meters from the end. It was a 3 kilogram beam, times 9.81 meters per second squared. And then R of tension. So the tension is going up like this, so the R is this whole length, so it's 4 meters. And the angle between the R and the F, this is 30 degrees. So on the bottom, that's like 2. And when you do this, you should get a tension of 206.01 newtons. Okay, makes sense? Now, in real life, for the beam, that would be question A. And question B would then say, what's the force the house puts on the beam? See, you don't get out of it that easy. You can't lose the force of the house. And to do that, now we know our force of tension. So now we can come back and solve the force of the house, because now we only have one unknown. And you have a couple of options. You could move your pivot point, but we don't know the angle of the force of the house. So I would suggest that you do sum of the forces. Sum of the forces in the x direction should equal 0 because this beam isn't moving. So in the x direction, there'll be F tension pulling one way and F of the house x pulling the other. Okay, and that has to equal 0. So that tells us F tension, the x component, will be cosine, will equal FHX. And we can find that. Don't change it to cos because we don't know what the angle is. So just leave it as FHX. You could find it, or you could just leave it like this and go to the sum of the forces in the y. In the y has to be 0 as well. Going up will be F of the house y. Also going up will be F tension y. And then going down, Fg of the sine, and going down, Fg of the beam. Okay? Is that really what I want to do? Oh, maybe you do want to find it. Oh, actually, okay, so you could write this as cos theta. And then, oh, no, you don't know that angle. So I guess find it, sorry. FHY will equal, take them over, m of the sine g plus m of the beam g, and then it's going to be minus ft, the y component will be sine theta. Okay, so FHY, I guess I need to fill numbers in, I avoided it for the other. 9 kilograms, 9.81 meters per second squared, plus 3 kilograms, 9.81 meters per second squared, oops,